Okay, so this says express the displacement current in a capacitor in terms of the capacitance and the rate of change of the voltage across the capacitor. Okay, so let me first tell you what the displacement current is. Okay, so what produces magnetic fields? A moving charge produces a magnetic field. So you see, here's a moving charge. This is the current density. Okay, let me answer this 1 second. This is my son. Hello, Beta? Yep. Okay. All right, I'm in class, so I'll call you back. Okay? Okay, bye. All right, so this is moving charges producing magnetic fields. What else is producing magnetic fields? Time varying electric fields is producing magnetic fields. Now look at this. This is mu naught times current density. So this fella acts like a current density. So this is called the displacement current. Okay. And again, where do you see time varying electric fields easily? In capacitors. Okay. So as the capacitor is being charged and the electric field is changing, that is acting like a displacement current. That's acting like a current. And you guys remember from the magnetic field, if you have a current like that, it produces magnetic fields like so. So similarly, if it has the same sign, if you have increasing electric fields like that, it'll produce a magnetic field like this. All right, so that's what the problem is about. All right. So express the displacement current in a capacitor in terms of the capacitance and the rate of change of voltage across the capacitor. So the displacement current we'll write like that. Okay, displacement current is epsilon naught del E by del T. Okay, so that's the direction of the current. Okay. And the electric field is in the capacitor is the V over D. Okay, so the voltage across the capacitance divided by the distance between the plates. Okay, so the displacement current, and again the arrow just tells you if the electric field is increasing in this direction, the current is in that direction. So now I'm just going to do magnitudes is equal to epsilon naught del by del T of V. And of course the plate distance, D is the distance between the plates, and that's not changing. So rate of change of the voltage across the capacitor. So the displacement current is epsilon naught divided by D times del V by del T. So again, all the important thing to remember is time varying electric fields behave like currents. Okay, so and how do the magnetic fields produced? You stick your thumb out in the direction of the current and your fingers point in the direction of the magnetic fields. Okay. So that's next problem is like that. So here is a current. This is a real current in the wire. What is it doing? It's charging the capacitor and it's producing this electric field. And it turns out that electric field is acting like a current, and that current will be exactly equal to this current. What is this current doing? It's producing magnetic fields like that, and this changing electric field is producing magnetic fields exactly like that. Yeah. All right, so the potential difference VT between the parallel plates shown is instantaneously increasing at the rate of 10 to the 7 volts per meter. What is the displacement current between the plates if the separation between the plates is 1 centimeters and they have an area of 0.2 meters square? Yeah. So the displacement, that was the current density. I'm sorry. this was the current density. All right, and the current displacement current is displacement current times the area. See, you guys see the mistake I made? The current density is what that is. Okay. All right, so. Okay, and this is, by the way, this is the capacitance of the capacitor. All right, so the displacement, what is the displacement current between the plates when the separation? It's epsilon naught A d del V by del T. Epsilon naught is 8.85 into 10 to the minus 12. Coulomb square. Newton meter square. Area is 0.2 meters square. D is 1 centimeters, which is 10 minus 2 meters. And del V by del T is 10 to the 7. Okay, so what will all the units turn into? Amps. Okay. Okay, so this is 10 to the minus 10, then becomes 10 to the minus 3. So the displacement current is 8.85 into 0.2 into 10 minus 3 amps. So .77 milliamps. Okay. If the electric and magnetic field strengths vary sinusoidally in time at frequency 1 gigahertz, okay, so your cell phone operates at, do you guys know what your cell phone operates at? Around 5 gigahertz. Yeah. Being 0 at t equal to 0, when E is that, and B is that, where are the field strengths next equal to 0? Okay, so here's the wave, okay, so E is 0 here, it'll be 0 there, okay, and this is one period, so half the period, okay, so it'll be 0 at t by 2 next. T by 2 is, t is 1 over frequency by 2, and so frequency is, they give you frequency is 1 gigahertz. Okay. So 1 over 2 times at frequency is 10 to the 9 hertz, 1 over seconds. So 0.5 into 10 to the 9 seconds. 0.5 nanoseconds. All right. When do they reach their most negative value? They reach their most negative value then. That is, this is t by 2, this is 3/4 of a t by 2. This is a quarter t by 2, half t by 2, 3/4 of a t by 2. Point 0.75 nanoseconds. How much time is needed for one complete cycle? Mhm. Okay. A radio station broadcasts at a frequency of 760 kilohertz at a receiver some distance from the antenna. At a receiver some distance from the antenna, the maximum magnetic field of the wave is 2.15 times 10 to the minus 11 Tesla. So the magnetic field in this wave is, what is the Earth's magnetic field? Yeah, -1/5. So this is about 1,000,000 times weaker than, okay? But so how do you detect it? Well, this is oscillating. The Earth's magnetic field is constant. Okay? So you're looking for the oscillating part. Field is detected. What is the maximum electric field strength? Okay. So remember, E max divided by B max equal to C. So E max is C times B max. 3 times 10 to the 8 meters per second times 2.15 into 10 to the minus 11 Tesla. Volt per meter. Okay, so the electric field strength is that. Okay, what does this mean? So if you have a dipole antenna that's a meter long, the voltage that will be induced in this dipole antenna is a millivolt, 6 millivolts. Okay, so that's what that means. What is the wavelength of the electromagnetic wave? So C is frequency times wavelength. Wavelength is C over. Frequency is 760 kilohertz. Okay, so that will be 0.76 times 10 to the 6, 300 divided by 0.76 meters. So the wavelength of this is 395 meters. Roughly from here to Mainland High School. That's the wavelength of this wave. At what distance does a 100-watt light bulb produce the same intensity of light as a 75-watt light bulb produces 10 meters away? Okay. So here's a bulb, there's the power. The intensity at distance r is how much light is passing per unit area per unit time. Intensity is power divided by what is the surface area of a basketball. So let's say imagine a basketball of radius r. The surface area is 4 pi r squared. So the intensity is that power spread over that area. All right, so what you want is, I guess, so you want the 75 watt bulb, 4 pi r square. You want the same intensity as the 100 watt bulb, 4 pi r 100. Okay. So r 100 square divided by r 75 square r 100 is square root of p 100 or p 75 times r 75. So the 100 watt bulb will produce the same intensity. This is 10 meters. So the 100 watt bulb will produce the same intensity at 11.55 meters that the 75 watt bulb produces at 10 meters. Yeah, which makes sense. The more power you have. I keep my umbrella in the trunk of my car, which doesn't make sense. You gotta know. And it's buried underneath stuff. Okay, a small helium neon laser, that's those red lasers that you see. Again, those are the helium. Has a power output of, well, those are solid state lasers, but they produce the same color. Has an output of 2.5 milliwatts. What is the electromagnetic energy in 1 meter length of the beam? So, in 1 second, so this beam will, in 1 second, the length is c, and the energy content, see, this is producing milliwatt, that is 2.5 millijoules. So this beam has 2.5 millijoules per second is milliwatts. Okay. So you use this laser, shine it for 1 second and let go. Turn it off. And so the length of the beam is equal to that. That's how, in 1 second, that's the length of the beam you emitted. And the energy contained is 2.5 millijoules, right? All right. Now you want to find the energy in 1 meter of this. So there's c meters, so the energy content, or the energy content of in 1 meter is 2.5 millijoules divided by 3 times 10 to the 8 meters. That was the length. So 2.5 into 10 minus 3 joules divided by 3 into 10 to the 8 meters. And so this works out to 8.33 into 10 minus 12 joules per meter. So we should actually really say energy per unit length, okay? Energy divided by length. So 8 times 10 to the minus 12 joules per meter. So what we calculated was you shine this laser and every meter has that much energy. Okay. So this problem says at the top of the Earth's atmosphere, the time average Poynting vector associated with sunlight has a magnitude of 1400 kilo, 1.4 kilowatt per meters. Okay. So what this means is, again, so you should be aware of this number. Okay, so we have sunlight reaching, and for every meter square, okay, so the intensity is 1400 watts per meter square. Okay, so the amount of energy falling is 1400 watt bulbs lighting falling every meter square. Here's a meter square. Okay. And you know, well, half of it reaches the surface on the average. All you have to do is harness about 1 part in 15,000 of this energy to satisfy all of mankind's energy needs. Just 1 part in 15,000. Well, you don't want to be harnessing it there. I mean, it's cheaper to harness it here. So 1 part in about, 7,000, reaching the surface of that. All right. So what are the maximum values of the electric and magnetic field of this intensity? So that's the intensity. And you will see A is E max, B max divided by 2 mu naught. Yeah, so I'll show you the formula. There's the Poynting vector. Okay. And so intensity is E max, B max over 2 mu naught. Okay. And you can, B max is, so if you want to, what is the maximum electric field? This is equal to, B max is E max over C. So E max square over 2 mu naught times C. Okay. So let's figure that out. 2 mu naught is 4 pi times 10 to the minus 7 Tesla meter amp. C is 3 into 10 to the 8 meters per second. And intensity is 1400 watts per meter square. All that to the power half. Okay. So this is the intensity of electric field in sunlight, okay? 100 kilometers above the surface of the Earth. All right, so this gives you 10, so we'll make that 10 to the 4 to the power half is 10 squared. So Emax is 10 square volt per meter. What is left inside is 2 into 4 pi into 3 into 1.4 to the power half. Okay, again, this is 10 to the 1 and plus 3, 10 to the 4. Okay. Thousand volt per meter. Okay. So that's the electric field in the sunlight in space, okay, close to the Earth. And B max is E max divided by C. So the amplitude of the magnetic field is about 1/10 the Earth's magnetic field. Now, what is the power radiated by the sun? Assume that the Earth is 1.5 times 10 to the 11 meters from the sun. Okay. So the again intensity at this point. So power. The intensity is power divided by 4 pi r square. So power is intensity times 4 pi r square. Intensity was 1400 watts per meter square near the Earth. 4 pi, and the distance is 1.5 times 10 to the 11 meters. That's 150 million kilometers squared. Okay, let's take your powers of 10. That's 10 to the 22, and we'll make that 10 to the 25. Okay, so 10 to the 25, and this is the meter square cancels with that, so you get watts. 1.4 into 4 pi into 1.5 squared. All right, so here's an interesting way to look at it. So here is the power of the sun, okay, and that's equal to 4 times 10 to the 24 into 100 watts. So this is 4 trillion 100 watt bulbs. That's how bright the sun shines. Trillion 100 watt bulbs.
Guess that's why you're not supposed to stare at the sun.
All right. And the sun is a pretty ordinary star. Okay, so a 2.5 diameter university communication satellite dish receives TV signals that have a maximum electric field strength of 7.5 microvolt per meter. Okay. So you guys have seen these communication dishes, right? So this dish is, the diameter is 2.5 meters. This is 2.5 meters. So you have a dish like this because the signal is weak, and then you focus all this into a tiny antenna, and then you get a large enough signal that you can process. Okay. So the weaker the signal, the larger the gathering area you want. So that's why telescopes have to be larger and larger the further out an object you're looking at, because the signal is weaker and weaker. Okay. I have a maximum electric field of that. What is the intensity of the wave? The intensity of the wave is E max square divided by 2 mu naught times C. You saw that formula. 7.5 into 10 to the minus 6 volt per meter square. 2 mu naught is 4 pi times 10 to the minus 7 Tesla meter amp, and C is 3 times 10 to the 8 meters per second. So the intensity of this beam is, all right, we'll take care of powers of 10. That's 10 to the minus 12, and that makes it 10 to the minus 5. And then this comes up, so minus 13, 10 to the minus 13 watt per meter square are the units for intensity. So this is 7.5 square divided by 2 times 4 pi. Oops. Into 3. So the intensity of this beam is remember the intensity of sunlight is about 10 to the 3 watts per meter square. So this beam is 10 to the 15, 16, 17 times weaker than the intensity of sunlight. 1,000 trillion times, or almost 1,000,000 trillion times. What is the power received by the antenna? Power is intensity times the area. Area is pi r squared. Okay. Area is this area of the disk. Okay.
Wouldn't it be the half of the sphere? The area?
No. So the antenna is like this.
Okay, so it's not like a spherical one.
Yeah,
I got you.
it's a parabolic shaped thing.
Okay.
So the power is and 2.5 meters is the diameter. We just found the intensity. Okay. So you see, the power will be larger the radius. Okay, you double the radius and you get 4 times the power. So even with a disk that large, the power you're getting is a trillionth of a watt, a third of a trillionth of a watt. Okay. And so you get that signal, and then what is the first thing you do? You amplify it. You're putting energy using a battery and stuff like that. Amplify the signal and then tease out the information from the signal. Oh, okay, so what is the power received by the antenna? If the orbiting satellite broadcasts uniformly over an area of this much, a large fraction of how much power does it radiate? Okay, so this is the intensity that's coming to the antenna, and this intensity needs to be all over the US. So so for part C, now we're going to, the satellite is, okay, that's the intensity. And now the area is the area of the US. Okay. So that gives it the power of the satellite. So the power of the satellite is I over area of the US. And the intensity was 7.5 into 10 minus 14 watts per meter square. And 1.5 times 10 to the So the power at which the satellite is broadcasting is 1 watt. All right, so why not make the signal stronger? Well, the satellite has to use solar panels to get its power and all that. Okay. So now you see satellite phones are quite hard because a phone has a very small area of gathering power. Okay? It essentially has to operate at that low intensity. You gotta have good electronics too. Yeah. So if you can carry around a dish, then you can have a satellite phone, cheap satellite phones. A microscopic spherical dust particle of radius 2 micrometers and mass 10 microgram is moving in outer space at a constant speed of 30 centimeters per second. So this is moving at velocity at 30 centimeters per second. Radius is 2 micrometers. Mass is 10 micrograms. Well, we're not going anywhere, so we might as well. A wave of light strikes it from the opposite direction of the motion and gets absorbed. Okay, so a beam of light gets absorbed. And remember, the beam of light, when it gets absorbed, it's exerting a force in that direction, so it'll stop this particle. Okay. Assuming the particle decelerates uniformly to zero speed in 1 second, what is the average electric field amplitude? So what is the electric field amplitude in this beam of light? Okay, so what you want to do is you want to stop this in 1 second. Okay, so let's calculate the acceleration first. The acceleration you need is delta V. Okay, this is the formula we are using. V is V naught plus A times T. Acceleration is V minus V naught divided by T. The final velocity is 0. Initial velocity is 0.3 meters per second. And you're stopping it in 1 second. So the acceleration you want is negative 0.3 meters per second squared, but the negative sign just telling you that the acceleration is in that direction. Okay. All right, so what is the force you need to apply on the object? Mass times acceleration. And that's equal to 10 micrograms. Micro is 10 to the minus 6, and a gram is 10 to the minus 3 kgs. So that's 10 to the minus 9 kgs. And then acceleration is 0.3 meters per second squared. Force. All right, so this is 3 times 10 to the minus 9 newtons. So the force that needs to be applied there. Okay, the force is pressure times area. And the area is the area of cross section of that, which is pi r squared. Okay, of the particle. So, and the pressure, so pressure is pressure is intensity divided by C. So if so pressure is intensity divided by C. Okay. So when you're absorbing, it's intensity divided by C, which is average intensity, which is E max square divided by 2 mu naught C times C times C. Bless you. Okay. So so now we can plug all of this information in and calculate the amplitude of the electric field in that beam that stopped the particle. So what was the force you needed? 3 times 10 to the minus 9 Newton. And the radius of that particle is 2 micrometers. All right. So let's take care of powers of 10. That is 16. And this is 16 as well, so that kills that. This is minus 12, comes up there, plus 12 to the power half, so 10 to the 6. Okay, what did we do wrong? All right. And then the rest of the stuff, 3 times 8 pi times 9 divided by 4 pi. So 6 times 9 is 54, square root of that. So what we are saying is if you shine this beam of light for 1 second on the particle, it'll stop it. But this is an electric field about 1,000 times greater than the Earth's, than the electric, than sunshine on space, Earth. So you have to be a lot closer to the sun. Okay. Is there a way you can check this answer real quick in the book?
In the book?
Or,
I just did it on my calculator, I got the same answer as you.
yeah, well, maybe you made the same mistake as I did.
That's true.
Right. I have like to take pictures of the questions, I have the other one up and it has the same answer.
Okay, all right.
If that's what you're asking.
Well, yeah. So to stop that particle, you have to be a lot closer to the sun. Because near the Earth, the electric field strength is 10 to the power 3.
67, right?
Mm-hmm.
Yeah, 7.34 times 10 to the 6 volts per meter.
All right. All right, so one last one. What is the frequency of a 193 nanometer ultraviolet radiation used in laser eye surgery? Okay, so C is frequency times wavelength. So what we'll do is we'll borrow 2, we'll make it 300 divided by that. That's 10 to the 6, and that coming up there, we'll make it 10 to the 15 hertz, and 300 divided by 193. So 1.55. That's the frequency. By the way, what is the visible range? 400 to 700 nanometers. Okay, so this is a UV light, as it says, 200 nanometers. Okay, so why are we using this?
Because our eyes can't detect it.
No. Okay, so this is the nanometer. Okay, so let's see. We'll say, so the wavelength is approximately 200 nanometer. So 0.2 into 10 to the minus 6 meter. 0.2 micrometer. A cell roughly is the size of a micrometer or a little more than that. So this is the 10th the size of a cell. So remember, in surgery, what you do is, here's your eye. Do you know what they do in laser surgery?
I have no idea. Shoot a laser in your eye.
Shoot laser in your eye. All right, so here's the eye. Okay, here's an object that you're seeing. So light bends the most when its speed changes. So this is light traveling in air, and your eyeball is essentially water. So when it hits the cornea, that's when the most bending happens. Okay, in fact, I believe 75% of the bending happens at the cornea. So you want to focus there. And 25% of the bending is done by the lens. So the lens does very little. Okay, so if you have to do corrective surgeries and you're not focusing properly because the cornea is misshaped, or the eyeball is misshaped or whatever. So what you want to do is you want to fix the cornea. Okay? So what you're going to do is, so here's your eyeball. You're going to cut off the cornea and peel it off like that. and then burn the cells here. And then put it back. That's right. Okay, so you're reshaping the cornea. What do you want? If you want to do fine work, you want a very thin beam. Okay? And the thinner the beam, the more you can reshape. So the smallest, okay, so, well, the smallest indentation you can make is roughly the size of the wavelength. So the smaller the wavelength you do, the smaller areas you can burn off. Okay. Yeah, so if you use visible light, the smallest corrections you could make were 400 nanometers, but this is 200 nanometers. Okay. Assuming that, so there you go, assuming the accuracy with which this electromagnetic radiation can ablate, meaning burn off the cornea, is directly proportional to the wavelength. Okay, so that's why.
Twice as accurate.
Yep. How much more accurate can this UV radiation be than the shortest wavelength? There you go.